we've already seen how to take a simple root, like the square root of 64, and rewrite it as a power, 64 to the power 1/2. Right? And we also know, based on our understanding of what a square root is, we know that the square root of 8 is equal, sorry, the square root of 64 is equal to 8. So let's take this up one more level. Suppose, for the moment, that I'm going to take the beginning and the end statements here. So 8 is equal to 64 to the power 1/2. And let's suppose that I take both sides of this equation and I just raise it to another power. So we're going to play the power to power game again. Let's say I raise both sides to the power 3. So first of all, starting on the left-hand side, how are we to understand what 8 to the power 3 is? What is 8 to the power 3? How do I find it? 8 times 8 times 8, exactly. Cubing something is just multiplying it by itself, a total of 3 factors. 8 times 8 is 64. 64 times 8 is 512. Okay, so don't sweat that arithmetic. That's not the point of this. Because what I'm most interested in right now is how we're going to think about what happens to this expression over here on the right. So if I take 64 to the power 1/2 and I raise that whole thing to the power 3, what's going to happen to those exponents? The 1/2 and the 3 right here. What happens when you take a power to a power?
Don't you add them?
Do we add them?
No.
Yeah, that's a classic rhetorical question. Yeah, no, we're not going to add them. How do I know I'm not going to add them here? What would this look like if I were to add them? 64 to the 1/2. So here's what I would say. I would add the 1/2 and the 3 if I were doing this. Okay. Because in this example, what am I doing to the two monomials?
You're multiplying.
I'm multiplying the two monomials. So in this situation, I do want to add these two exponents. But instead, what am I doing up here? What kind of arithmetic am I doing to this monomial? I'm raising it to another power. So another way that we could think about this, so let's play the same game with this as we did with the 8s over here. To raise 64 to the 1/2 to the power 3 is to multiply it by itself 3 times. So 64 to the 1/2 times 64 to the 1/2 times 64 to the 1/2. And so I can see that as a multiplication. And when I multiply monomials, I can add the exponents. But what am I going to end up adding in this situation? I'm going to add a 1/2 plus a 1/2 plus a 1/2. So how many halves do I end up with?
1 1/2.
Yeah, I end up with 3 halves. Or 1 1/2 if you like, but I'm going to stay away from using mixed numbers. So what I end up with is 64 to the power 3 halves. But here's the cool thing. Based on what we knew about 8 and 64, we now know that there's also this relationship between 512 and 64. So my point is, knowing that the square root of something is that same thing as that quantity raised to the 1/2 also tells us how to raise quantities to other kinds of fractions. So we might imagine a problem coming at us that asks us something similar. So the question might be something like, what is, let's say, what is 9 to the power 5 halves? So how are we to understand now how to evaluate this exponential expression? How do you raise 9 to the 5 halves power based on using the sort of the tools that we used up here? What do you think? What are some ways of moving that forward? Work this backwards. How would I start?
It's 9. I know you multiply.
Okay. So I want to somehow see this as a power raised to a power, right? So I want some exponent there, and I want some exponent there. And when I multiply those two exponents together, I want their product to be 5 over 2. Right? 5 halves. So in our last example, that meant that we had a 1/2 inside of the parentheses, and then on the outside, we put a 5. Let's try it and see if that helps advance our puzzle here. Right? So I'm just taking apart the number 5 halves into 1/2 times 5. Right? So now why is this helpful? Yeah. Yes, right, exactly. So if we wanted to unpack this arithmetic, 5 over 2 is the same thing as 5 over 1 times 1 over 2. Right, so I'm sort of taking apart this fraction. Remember, when we multiply fractions, how do you multiply fractions?
Across.
Straight across, exactly. So that's how I know that 5 over 2 is the same thing as 5 over 1 times 1 over 2. I'm just multiplying straight across. 5 is 5 times 1, and 2 is 1 times 2. But 5 over 1 is, in fact, a whole number, 5. So that's the arithmetic behind why we can take apart 5 halves into 1/2 times 5. But now, why is this easier to understand? What do I have inside the parentheses? What is 9 to the power 1/2? Or what's another way to understand what is 9 to the power 1/2?
The square root of 9.
Exactly. Just remember what it means to raise something to the 1/2 power. It means take its square root. So while exponents are easier to do arithmetic and algebra with, radicals are easier to think about. Right? Radicals are easier to do mental computation with. So there, I'm just going to reimagine 9 to the 1/2 as the square root of 9. That's what it means. Right? And 9 just happens to be a number that has a nice square root. What is the square root of 9? 3. Because 3 squared is equal to 9. And so now we've whittled down our arithmetic problem from one that has this sort of nasty fraction up in the exponent to now remembering what that fraction in the exponent actually means. It means that we can cut our 9 to the 1/2 down to size as the square root of 9. And now it's just a problem of raising a whole number, 3, to a whole number power, 5. And how do we find 3 to the power 5?
3 times 3 times 3.
Yeah, just multiply 3 by itself a total of 5 times. And so you churn through that arithmetic, and you get an answer, 243. So the point here is that just knowing how to rewrite a simple radical using a fractional exponent also tells us how to interpret any expression that has a fraction in its exponent. Is we can just run the process in reverse and take apart that fraction so that we understand that what's really happening is we're doing two things. So just to kind of right over top of what we just did. When I have this fraction up here in the exponent, it means that I ended up doing two things. First taking a root, and then taking a power. And the root that I take ends up having the index given by the denominator of this fraction. So the denominator was 2, so that's why we ended up with a square root. And the power that I take afterwards is dictated by the numerator. So this 5 ends up explaining why we then take the 5th power here at the end of it. Our last example here, let's do 36 to the 3 halves. All right, so what have you got raising 36 to the 3 halves power? What did you do first? Right, so you took that 3 halves apart into 36 to the 1/2, done first. And then after you take that, what do you end up doing with it afterwards? To the power 3, right. So we just took the denominator of the fraction and put it on the inside of the parentheses, and we took the numerator and we pulled it out. And that's useful because how do we understand what 36 to the 1/2 means? It's the square root. Square root of 36. And the square root of 36 is 6. So that's a nice number square root. So that when the denominator has done its work, it's cut our 36 down to a 6. And now we apply the numerator to find out we need to raise 6 to the third power. And so that's 6 times 6 times 6. There's 216.